All right. I will begin. If I start too late, I'll have to go later, you know. Let's see here. Heavenly Father, we thank you for this day. Again, I thank you for these students. And just pray you just guide our work today. Help us to glorify you in what we do. And just to learn more about complex analysis. Lord, in your name I pray, Lord Jesus. Amen. Okay, so I got a little hung up on an argument at the end of last class. And I want to just talk about it again at the risk of, getting confused again. But it's okay. So this is... the question is the Laurent decomposition. All right, so what we're given a function which is holomorphic on an annulus. All right, so the function is given to be holomorphic on this annulus, which I have shaded green, which I should have chose a different color. The green never shows up worth anything, but if you can use your imagination, it's shaded between here and here. And inside the dotted lines. So that's where we're given that f is holomorphic. And so since f is holomorphic on that annulus, we can apply Cauchy's integral theorem. All right, so for any z that's in there, and we're looking specifically at a z which is between the blue and red circles. All right, so we have modulus of z minus z naught is less than or equal to, well, not less than or equal to, it's less than, it's greater than r, it's less than s, that s is less than sigma, and that r is greater than rho. Rho and sigma are the inner and outer radii on which we're given that f is holomorphic. All right, so for this z, for such a z, all right, for such a z that again the z would be between the red and the blue circle, we can apply Cauchy's integral theorem. All right, and so Cauchy's integral theorem here says that f of z, all right, in other words, the value of f at any point in there is given by what? By the integral of f of w dw over w minus z, like that, right? This is Cauchy's integral theorem. The reason I have two integrals is why. Can you explain? Why are there two integrals?
There?
Yeah.
There?
Yeah, why?
Well, you need to subtract one.
What?
Well, it's necessary to subtract one of them because there's two circles.
Right,
The area in between them.
well, it's not area, but there's two, come on. There are, oh man, son of a gun. That worked earlier. Yeah, I guess just, I'll have to go to a more basic technology. There we go. Watch. So this is the integral around the outer boundary, and that's the integral around the inner boundary. It would be clockwise oriented in terms of the natural orientation, but since I counterclockwise oriented the circle, that's why I put a minus there. And so that's, again, Cauchy's integral theorem. It says for a domain, an open connected set, the integral around the boundary of that set is equal to integral around the boundary of the function divided by w minus z multiplied by 1 over 2 pi I is equal to f of z for any z in that domain. This is Cauchy's integral theorem. So applying that to this annulus, where we're given that the function is holomorphic, we have this expression. And then the argument, okay, so at the moment that's only for z between the red and the blue circle, all right? But then the interesting thing is you can analytically extend those formulas, f0 and fz, to a larger context, all right? So notice that if we define f0 of z equal to 1 over 2 pi I, integral around w minus z naught equal to s, f of w over z minus w minus c dw, then if you look at that formula, where is the circle? Where's that S circle? It's this red circle, right? So if you look at this function, right? If you look at that, it doesn't face the division by 0 inside the red circle. Because we're looking at W on the red circle, I never hit the Z, which makes it singular. Which means that if we want to, we can observe that in fact this defines a holomorphic function for modulus of Z minus Z naught less than, S, I suppose, right? So as long as because I can throw in those points as well. Even though, and this is the thing I was getting hung up on last time. I was like, but I don't know the values of F inside the dotted line in the middle. I'm only given that F is holomorphic in the annulus, right? But notice that while Z could be taken from inside the dotted circle, this formula only involves F where? Actually on the red circle. See, so it doesn't even matter that I don't know any information at all about F inside the dotted circle. I can still meaningfully calculate this integral, and so I can extend it for Z. Again, the formula here only holds in the annulus, but this taken on its lonesome goes all the way to the center. And likewise, if you look at F1 of Z equal to the 1 over 2 pi I, minus 1 over 2 pi I integral over modulus of W minus Z naught equals to R of F of W dW over W minus Z. This is, holomorphic for modulus of Z minus Z naught greater than R. In other words, outside of the blue circle, that doesn't get into trouble with Z. See, because we're not going to have division by 0. Okay? And so, since you don't have division by 0, and we're only taking values of F on this circle where we're already given that it's defined, that's fine. So this, in a nutshell, is the central part of the proof of the Laurent decomposition, namely that if you have a function which is holomorphic on an annulus, then as we argued last time, there's a unique decomposition of that function into an F0 which is analytic, all the way to the center of the disk, and an F1 which is analytic outside the inner circle of the disk, all the way out to infinity. Now, those expansions, they don't have to match F of Z outside of the disk on which F is holomorphic. Like if F had another definition that extends past the annulus, there's no guarantee that these holomorphic extension, that these formulas have any connection whatsoever to F outside those contexts. All right? So we have to kind of keep that in mind. Now, so as I just get to where we got to last time, we discussed that because F0 is holomorphic inside, that means that you can write this as basically the sum n equals 0 to infinity of like a sub n Z minus Z naught to the n, whereas this is holomorphic for Z minus Z naught greater than R, and so that means that you could write this as the sum n equals minus 1 to minus infinity, actually, of a sub n Z minus Z naught to the n. And here I'm using the fact that the expansion out on the outer annulus is in fact assumed to be analytic at infinity. And because it's analytic at infinity, that means we have an expansion of it in terms of reciprocal powers. And also, because we're normalizing it, we've normalized it so that the part at infinity is 0, like f1 of infinity is 0. That's why I don't have to throw in, I have no overlap between these two formulas. So you put them together, and we have what's called the Laurent series. The Laurent series for a function is a sum of both powers, and positive and negative powers, reciprocal powers you could call them. And by the Cauchy integral formula, we also have that the a sub n is actually 1 over 2 pi I times this integral. So we even have a formula for the nth coefficient of the Laurent series in terms of the integral. That formula is most interesting in the case that we're, at n equals to minus 1, in which case we just have the integral. So let me put this away, and that's the backdrop for this lecture, okay? I'll probably come back to the projector here eventually, but I want to write some things out at a slightly less breakneck pace here. So, all right. So there is such a thing as a Laurent decomposition for any function that is holomorphic on some annulus. All right. And so we should talk about how this all works. And we need to make some definitions in light of this expansion. And so I will do that. So this brings us to section 9.2, all right? So I need to define some things carefully. Definition. F has an isolated singularity at z naught if there exists r greater than 0 such that f is analytic on the punctured disk. Oh man, I just remembered I forgot to bring a toy with me today. Son of a gun. I was going to show you guys something. Oh well, next class. It's okay. It was more to do with the Poincare, not Poincare, I'm an idiot, the Riemann sphere. But anyway. So there we go. That's an isolated singularity. That means that the badness is isolated, all right? If you're close to the point but not at the point, it behaves, all right? And so if we just think about this, so here's like z naught, right? So there's some kind of disk, right? And radius r here, right? And f is an element of the holomorphic functions at z naught, right? There exists some open disk on which, that's not quite true, is it? Why is that not true? Oopsie, I can't say that, can I? Why can't I say that? What don't we have? Z naught itself, right? So this is not generally true. That's why our context is new. Right? Now it could be the case, right? I haven't actually said anything in this definition demanding that f is not defined at z naught, right? So given my current definition, it could be that f is holomorphic at z naught. That would fall under the first case of what I'm about to define. And I don't really like that. I would really like for the singularity to demand some kind of like I would almost prefer, if I'm going to call it a singularity, like I think a better definition would demand that f of z naught not be defined. That's how the usual usage is, because if f of z naught is defined, and f is holomorphic at z naught. The usual language is to say that that's an ordinary point. But anyway, I'm pretty sure I got this definition from Gamelin, so it's his fault. Anyway, so here we go. Number 1, if f of z equals to the sum over, I'll use n equals 0 to infinity of a sub n times z minus z naught to the n, then z naught is removable singularity. I can't spell removable. Or maybe I can. I don't know. Removable singularity. Number 2, let big N be an element of the natural numbers. If f of z is equal to, I guess I'll use k now. I now know why I was using k. K equals minus n to infinity of a sub k, z minus z naught to the power k. Then z naught is a pole of order n. Oh, there is a little bit more. I forgot a term and condition here. What am I missing? What do we need to know about a sub minus n? That's right, yeah. A sub minus n not equal to 0, right? We have more special language here. If n equals to 1, we call it a simple pole. Just like we had a, remember we had if a 0 was just order 1, it was a simple 0. And if it was order 2, we had a double 0. That terminology persists here. Simple pole is this. Double pole would mean big N equals to 2. And then 3 is a scary one. If f of z is equal to a sum, k equals minus infinity to infinity of a sub k times z minus z naught to the power k, where a sub k is not equal to 0 for infinitely many k less than 0, then z naught is an essential singularity. All right? So these are the different types of singularities that we run up against. These are the different types of isolated singularities we run up against. And the fact that this is all that's possible follows immediately, logically, from the Laurent decomposition, right? Once we have a Laurent decomposition, we have a Laurent series. And once you have a Laurent series, you can think about what's possible. It's either going to be that there's infinitely many negative reciprocal terms which are non-trivial, right? Or there's finitely many, or there's none. That's it. That's the trichotomy. And so for case 1, you see case 1 would include the case that f was holomorphic, right? Now, let me give you some examples of each before we talk about the properties much. So example 1, standard example, like this is the example, sine of z over z, all right? So that is singular where? Well, that's singular at, the, whatchamacallit? Yeah, z equals 0. The origin, right? Cool. And, but how does this go? Oh, by the way, Laurent series are uniformly convergent on the annulus on which they represent the function, and therefore they enjoy all of the usual term-by-term integration and differentiation, rearrangement, multiplication of series, like all that jazz. So this makes sense. Right? And so forth. So what you got? You got yourself 1 minus 1/6 z squared plus dot 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 dot. Therefore, z equal to 0 is a removable singularity. All right? So far, so good. And what does that mean? That means if we wanted to, we could define this thing to be g of z, right? For all z, you know? And then we would have that g is an element of the holomorphic functions at 0, right? It is indeed a holomorphic function at 0, even though technically f of z is not even defined at 0. That means it's a kind of stupid singularity. It's a removable one. It's just an artifact of a bad formula. We can just cancel out. It's the hole in the graph for complex variables is what it is, all right? So a lot of people, they won't even like say things like f of z is sine z over z for z not equal to 0, and f of, you know, and then f of 0 is equal to 1, right? That would be the proper way to define f, or maybe the proper way to define g, right? G of z could be more properly defined like this, right? G of z is equal to, well, sine z over z for z not equal to 0, and 1 for z equals to 0, right? There you go. G is in fact an entire function, right? But what people typically do is just say f of z is sine z over z and say it's entire. Because it's understood that you remove the singularity at 0, right? And the people who write a lot of complex variables, they kind of aren't interested in this, and they just kind of suppress this nuance. Okay, anyway. Example 2, I guess we can get more mileage out of this example, but what if we had f of z equals to 1 minus cosine of z divided by z to the 4th? What would that be? Well, let's see here. 1 minus cosine z is what? It's 1 minus, you got 1 minus 1/2 z squared plus 1 over 4 factorial z to the 4th minus 1 over 6 factorial z to the 6th, and so forth, right? And that all is divided by z to the 4th. So how does that work out? Well, you've got the 1's cancel, and z squared over z to the 4th is, so I've got a what? 1/2 1 over z squared. Then what? Minus 1 over 4 factorial that, and then plus 1 over 6 factorial z squared plus dot 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 dot. So what is this? This would be an example at z equal to 0 is a singular point, right? And what's this one? Z not equal to 0 is pole of order n equals to what? Nobody? So all you got to do is you look at the Laurent expansion, which is right here, and the highest reciprocal power that appears tells you the order of the pole. Here it's 2, just that. If you want to, you could think of a removable singularity as a pole of order 0, but people don't typically say that, but maybe we should. Then there'd just be 2 cases. Finite pole or essential singularity, which is my next example. Example 3, if we had something like, oh, I don't know, f of z equal to e to the 1 over z, well, that's 1 plus 1 over z plus 1/2 over z squared, 1/2 of 1 over z squared, right? Plus dot 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 dot. I mean, if you like, it's equal to the sum n equals 0 to infinity of, 1 over z, 1 over n factorial, my bad. Man, these boards are really messed up lately. 1 over n factorial z to the power n. There's a formula for it. If you like, I could rewrite that kind of more in the style of my definition. Sum k equals, well, let's say minus 1 to minus infinity of 1 over k factorial z to the power k, right? Plus 1. So this whole part of infinitely many singular terms, right? Infinitely many reciprocal powers at 0. This is an essential singularity, all right? Any questions so far? No? Let us discuss the properties of these. I guess it might be good. Well, you guys, your choice. Would you like me to find a Laurent expansion of a function in a non-trivial fashion? Or do you want me to go over the theorems first? What's your preference? Example or theorems? All right. You chose wisely. All right, I think we can get rid of this definition now in the middle, so let's do that. I said it once, which means you have now memorized it and understand it completely. Those are the rules of the course, so. Isn't math fun? Let's see here. So here's an example. Let's actually work on a particular function. Let's say f of z is, I don't know, z over z squared minus 9. All right. And let me not have the z upstairs. Let's just do like 1 over z squared minus 9. So what this function here as singularities where? Z equal to what? Yeah, 3 and negative 3. So let's draw a picture and kind of just think about our life. So we've got 3 and minus 3 as we know they're going to be trouble spots, all right, for this formula. All right? Now, where would you guys like to look at the story of the Laurent series? Let me suggest that we center it at 3. Okay? That's an interesting point to center it at. But we could pick any point and center it around any point. The story would be a little bit different if we did. I'm almost tempted to try to center it around I and see what happens there. No, I'll do 3. So if we look at 3, we kind of expect that we're going to have like this as our scope if we center at 3 for the Laurent series. So let's see how that goes. So the goal, well, first of all, I probably should use partial fractions on this. You guys tell me how to do partial fractions for here? I can write that as like a over z plus 3 plus b over z minus 3, right? And I get what? And let's see here. I mean, the proof's in the pudding, I suppose. If it works, it works. If I put in z equal to 3, I get what? 1 equals to 6b. If I put z equals to minus 3, I get 1 is equal to minus 6a. I see now that my original formula was missing a 6 right here. There we go. That's better. Fixed. You're not allowed to do that on tests. That is one of the the privileges that you get once you earn a PhD in math. Like, that is one of the things you're allowed to do. And you learn a secret handshake that I'm not allowed to share with you. But anyway. So f of...
Yes, it would be having.
What's that?
You have to tell us that we got it right.
If what?
If we guessed the handshake, you have to tell us we got it right.
Oh. I guess that's true. But since I just made that up, it's impossible to guess. Let's see here. You're like, wait a minute, that means that the handshake is the empty handshake, which I already know. Therefore, you owe me whatever you said that I promised me. Dang it.
This is not the joke.
Math majors.
It means I'm a PhD now.
That means you're a PhD now. Oh no, I just gave everyone a PhD in math. No, my job security is dead. Actually, who am I kidding? Anyway, so yeah, that's that. Now, okay, so if we're trying to expand around 3, one of these things is already done. See, this is a term in the Laurent expansion. That's it. This, on the other hand, needs to be worked on. All right? But I can already tell you from this expression and the theorems I haven't covered yet that this function has a simple pole at 3. Because 1 over z plus 3 is in fact holomorphic. So anyway, let me do this. All right, so 1 over z minus 3 plus minus 1 over 3. Factor it out to 3, okay? 1 plus z over 3. And so what we got? 1 over z minus 3 minus the sum, n equals 0 to infinity of minus 1 to the n over 3. Oh man, I'm like, good grief. I tell you, I have been making the stupidest mistakes today. What I'm doing is not wrong, it's just pointless. Because I'm trying to expand where? At 3, right? So I need to create z minus 3s. How do I get a z minus 3 from this? I do 6 plus z minus 3, right? Now I have got to factor out a 6. All right. And now I can do geometric series. It's always geometric series pretty well, it's a lot geometric series. So minus the sum n equals 0 to infinity of minus 1 to the n divided by 6 to the n plus 1. I'm going to throw a plus 1 in here and change that minus to a plus for good measure. Z minus 3 to the n. There you go. Voila. Laurent expansion. That is the Laurent expansion for f of z inside the red dotted circle. All right? Notice, by the way, this works exactly as the thing I was talking about today, right? At the start of class. Do you see this? This right here is my f0. This right here is my f1. In the sense of, do you notice that 1 over z minus 3, it is where? It is holomorphic on the entire complex plane, all the way out, even at infinity. Okay, at infinity it's not holomorphic, it's, is it? Wait a minute. Yeah, no, at infinity it's holomorphic. Okay, so that one is, the f1 goes on out, all the way out, and f0 is, it is certainly holomorphic inside the outer radius of consideration. So the red dotted circle would play the role that I think I called it sigma in what I started with today. In this one, rho, quote unquote, what is rho equal to in this one? It's 0. That's a possibility, all right, when you look at the careful statement of what I was starting with today here. Rho could be 0 and sigma could be infinity. In fact, sigma will be infinity for the next case of consideration. So the next case of consideration, so again, this formula is only good for 0 less than absolute value of z minus 3 is less than what? This step right here, what does it need to make that go? What do you need? You need the radius of the geometric series to be less than 1 in modulus, right? Which means that you need z minus 3 over 6, modulus to be less than 1, which is to say you need z minus 3 to be less than 6, right? Now, okay, so suppose we have what? What's the other case? Man. Otherwise, we have what? We have the modulus of z minus 3 what? Greater than 6, right? So if modulus of z minus 3 is greater than 6, then we have f of z is equal to 1 over z minus 3 minus 1 over z plus 3, right? So it's still the case that 1 over z minus 3 is the singular part, okay? But now I can't make that geometric series step I did last time. I have to play a different game. I have to make this in terms of like 1 over z minus 3 is the game I want to play here. I want to rewrite it in that way. How do I do that? How can I rewrite this thing? Goodness gracious. Well, the thing is I can't do that exactly because I don't have the condition that made that work last time, yeah? Watch me not have this example in my notes. I know it's in your homework. But you haven't done that homework yet, so you can't help me, right? All right, I need a creative leap here. How can...
Take the reciprocal, express it as a power series in z minus 3, and then basically do like polynomial long division with the dividend being 1, and then get like an infinite Laurent series basically.
Maybe. So you're saying... Sorry. Rats. So you're, I'm sorry, I'll track with you here in a second. So you're saying, look at that as 1 over z minus, 1 over, no, that's not it. That is 1 over. Right? Which is stink. I think what you're saying is what I'm trying to do, Ben. But how do I do it?
You could just do 1 over 6 plus z minus 3, and then divide.
Wait. Hold on. 1 over what? 6 plus?
6 plus.
Okay, so now we're back to what Ben told me.
Yeah, and then
I mean Jeff, rather. Yeah. And then what?
divide the denominator into 1.
Oh, thank you. You have helped me. Now I remember. Divide. Just stupid. It's just stupid. You just divide the top and the bottom by z minus 3. That's all. So 1 over z minus 3 upstairs, and then 6 over z minus 3 downstairs, plus 1. Ha ha! Geometric. See, because this I can pull that out, and then I've just got 1 over 1 plus 6 divided by z minus 3. See, now it's thankfully I don't have to, like, we could do what you were saying, but I don't want to do it. And now it's geometric. And what is it? Well, all right. Let's see here. The sum minus 1 to the n. I guess it's 6 to the n, isn't it? Did I do that right? Yeah. 6 to the n. Yeah. Z minus 3 to the n. Now to go from now, I should be careful. It's not to the n here. It's to the what? Well, I'm sorry, guys. I'll get it. It's not wrong, but I put a minus n there if I did write it that way. I'm going to write it in the denominator like it is. Z minus 3 to the n. All right. N equals 0 to infinity. To make this step, I need that the modulus of 6 over z minus 3 is less than 1, right? Which we have, right? Because the modulus of z minus 3 is greater than 6. If you want, I can write it the other. Okay, anyway, put it all together. We've got 1 over z minus 3 plus the sum n equals 0 to infinity of minus 1 to the n plus 1, 6 to the power n, divided by z minus 3 to the n plus 1. All right. And there you go. That's the Laurent series. Outside of the red disk. Now, question is, it looks like we've got infinitely many reciprocal terms here, huh? Right? Have we changed the kind of singularity? It was a simple pole in the inside. Now is it an essential singularity now?
You said this is outside of the curve?
Outside of the red circle, yeah. That's where this expression holds.
Well, then it wouldn't be essential anymore?
The answer is that the essential, like the definition of singular point, respected the Laurent decomposition near the point. This is not the Laurent decomposition immediately adjacent to the point in question. The Laurent decomposition on the deleted disk centered at 3 was what we first did. So this Laurent decomposition doesn't answer any question about the nature of the singularity at 3. It is a Laurent decomposition. It does have a singular part, which is, like an essential singularity, but it doesn't matter. It's not where we need to look at to decide the type of singularity. The type of singularity is decided by the deleted disk around the singularity, but we're not there For this, we're outside of the red circle. So my question is based on a confusion that the Laurent decomposition has to have the same form in the different annuli surrounding a given singularity, and that just is not the case. The nature of the Laurent expansion on the different annuli, it'll be different in each annulus. So, yeah. Yep. Now, we can ask the other question is, what about infinity? How do we define, singularities at infinity? Do you guys remember how we define analytic at infinity? We said f of z analytic at infinity, right? If g of w equals to f of 1 over w, analytic where?
0.
Yeah. So guess what the definition for a pole at infinity is?
A pole at g. So f of z has a pole at
Yeah.
at infinity. If g of w equal to f of 1 over w has a pole at w equals 0.
Exactly. So, for instance, example 5 here, check this out. If we have f of z equal to sine of z, sine of z is a great example. This is an entire function, right? This is an element of the holomorphic functions on the entire complex plane, right? That means it has no genuine singularity anywhere. All right? Any place that you were to, any place you looked, there would be a removable singularity in the most stupid sense possible. Okay? This has no genuine singular points. And let's just say a genuine singular point is either a pole or an essential singularity. However, at infinity, what happens? Check this out. G of w, sine of 1 over w, right? Oops. That is the sum n equals 0 to infinity minus 1 to the n over 2n plus 1 factorial, w, 1 over w to the n, 2n plus 1 rather, my bad. That is very much an essential singularity of g at 0, right? So w equals to 0 is essential singularity of g of w. Therefore, f has essential singularity at infinity. All right? It's going to turn out that if we were to look at the external, if we were to think about this Laurent decomposition in the previous example, what we'd learn is that the reciprocal term here ends up being a pole of order 1 at infinity. If I remember right. Wait a minute. Other way around. Oh, let me shut up. I'm not sure what happens, actually. Let me not blather about that at the moment. Yeah. We stick with what I know. I'll leave the rest for your homework. So, anyway. Any questions at the moment? Yeah.
So, does an essential singularity mean you have to remove that point in order to deal with the function?
Well, essential singularities just don't have. Well, let's talk about it. What's the difference between a remove? How would you? That's the natural question to ask. Is what is the actual difference between an essential singularity, a pole of order n, and a removable singularity? How do you characterize, a holomorphic function which has that type of singularity near the point? Like, what can we say? All right. So I'll tell you what. I'm going to project in a second. I'll just tell you in words. A removable singularity, it turns out that the function has to be bounded. The modulus of the function is bounded near the point. If the function is bounded near the point, it has a removable singularity. If, on the other hand, the modulus of the function necessarily goes to infinity from any approach at the singularity, it has to be a pole of order n. And then the essential singularity, the way it behaves is weirder. It can approach some ways of approach. It will give you an infinite modulus, but there are other ways that it might just be equal to a constant. Let me show you that example before I get into the projection of the theorems here. Now the proof of all those things, it's really just simple calculations with the Laurent series, honestly. And well, we'll get to them in a second, but let me just show you the weirdness of the essential singularity and how it behaves. So I think e to the 1 over z is a nice one. If we look at f of z equal e to the 1 over z, of course z equals to 0 is essential singularity, right? Because if we look at the Maclaurin expansion for this, it just goes on and on and on, right? There's infinitely many reciprocal terms in the expansion centered around 0. So what happens if I look at the modulus of e to the 1 over z? What's that equal to? Let's see here. What's that? That's the, let's think about a simple case. What if we look at like z equal to iy, for instance, where y is a real parameter? What would you get? Ooh, huh. Well, I guess that's modulus of e to the I over y, and that's equal to 1 if y is not equal to 0, right? Because it's an imaginary exponential which has modulus 1. So if I approach the origin along the imaginary axis, this goes to 1, right? So this way, or this way, I get limit 1 for the modulus of f of z. But I don't know, there's more we could say. Like you can actually, I'm trying to think how you can do it. Oh, I forget there's a couple theorems about essential singularities. Theorem of Casarati-Weierstrass and the Picard theorem. I think essentially the theorem is that you can get the values of the function to go to any complex number that you like, except possibly 1 for essential singularity. So for this one, there's only one thing you can't get out of e to the 1 over z as you approach the essential singularity, namely 0. But any other complex number you can approach by taking an appropriate sequence. I think it's stronger than that. I think you can find a sequence of z's on which the essential singularity is constant at that value other than that one value, which happens to be 0 for this one. Anyway, essential singularities are weird, all right? But poles of order n, on the other hand, are super nice because what was the theorem we had? The integral, how'd it go? The integral of f of z, my bad. Forgot my, I'll get it eventually here. So if I have f of z dz, say around modulus of z minus z naught equals to r, I can look at that as what? If z naught is an isolated singularity, what is this? This is the integral over the Laurent expansion, right? Close to the, like suppose that z naught is an isolated singularity of f all right? And suppose that the Laurent expansion exists at least up into R, okay? So suppose we're within the context of the Laurent expansion. The Laurent expansion holds within this circle, okay? But not the center, of course, is a singular point, so it's not actually there, but outside of there it does, okay? So on this punctured disk, and maybe R is in here, all right? Then this is what? This is the sum of a sub n, z minus z naught to the n power dz, right? N equals minus infinity to infinity. But if, well, anyway, it doesn't actually matter if it's a, I think it's still true for an essential singularity, actually, now that I think about it. Huh. I better get the notes back out. But this, of course, works out to what? This is just, 2 pi I a sub minus 1. Because you guys have already worked out that the integral of z minus z naught to the power m or power n around a circle centered at the, centered at z naught, it's always 0 except for the one special case of the reciprocal power. And since the Laurent series uniformly converges, you can flip the order of integration and summation, and that's all you get. That means we can calculate the integral of a function that's singular inside some circle or something by simply calculating the Laurent expansion around the singularity and picking off the -1 coefficient. For example, if I was to integrate, I don't know, e to the z over z minus 1 dz over, say, modulus of z minus, well, I could just say over the circle of radius 10, all right? Then this, what is the Laurent expansion centered around 1 for this? We do what? E to the z minus 1 plus 1. And so what you got there is 1 over z minus 1 times e times the sum, n equals 0 to infinity, of z minus 1 to the n over n factorial, using the Maclaurin expansion for e to the z minus 1. And lo and behold, we've got e over z minus 1 plus the sum n equals 1 to infinity of z minus 1 to the n minus 1 over n factorial. And I think I need to multiply the e through there, right? Put an e somewhere in here, right? There you go. That's the Laurent expansion centered at 1 for this function. Where is it applicable? What's the domain for this Laurent expansion? So this is actually the Laurent expansion on the punctured plane. Everything except for 1. So I can think about basically just plugging this, right, into here, chunk, and what do I get? I get 2 pi I times the coefficient of the -1 term, which is what? So my quote-unquote a sub minus 1 here is e. This integral is 2 pi I e. Done. What do you think of that? You're like, well, isn't this just Cauchy's generalized integral formula? Well, it is, but it's more. See, because what I'm proposing is that we can calculate the Laurent series for a function